Your heart doesn't pump in a smooth stream. It fires in sharp bursts, once per beat. So here's the strange part. The pressure in your arteries doesn't spike and crash with every beat. It stays high and falls off gently even while the heart is resting. What smooths it out? Why doesn't it crash between beats? The answer is a century-old idea called the Windkessel, and the whole thing collapses to just 3 numbers wired together like a little circuit. By the end of this video, you'll have derived all 3 from scratch, and you'll know exactly which one to blame when a simulation's pressure comes out wrong. Here's the idea. Don't model every vessel, lump the whole downstream tree into a few elements, and borrow the language of circuits. Pressure plays the role of voltage, and flow plays the role of current. The two obey the same kind of equations, so every circuit element we know has a blood flow twin. We need just 2 of them, plus 1 more. First element, resistance. The smallest vessels, the arterioles and capillaries, are narrow, so pushing blood through them takes pressure. Double the flow, double the pressure drop. That linear relationship, pressure equals resistance times flow, is exactly a resistor. Second element, compliance. The big elastic arteries, the aorta especially, balloon out when pressure rises, storing some of the blood, then squeeze it back out as pressure falls. Compliance measures that, how much volume the vessel takes in per unit rise in pressure. Storing charge when voltage rises is exactly what a capacitor does. So, the elastic arteries are a capacitor. Put them together. Flow comes in and meets a junction. Some of it inflates the compliance. The rest drains out through the resistance to the veins. Balance the flow at that junction. Inflow equals the flow into the compliance. C times the rate of pressure change, plus the flow leaving through the resistance, P over R. That single equation is the 2-element Windkessel, and it makes a clean prediction. In diastole, the valve is shut, inflow is 0, and the pressure just decays exponentially with a time constant R times C. That decay is exactly what you read off the echo to pin down RC. The 2-element model is good, but it has a blind spot. The moment the aortic valve opens, blood has to surge into the aorta, and the aorta itself pushes back on that sudden flow. The 2-element model has nothing for that, so it gets the pressure wrong at the very start of each beat. The fix is 1 more element. Put a small resistor in series, right at the inlet, before the compliance chamber. It's the characteristic impedance, ZC, the aorta's own resistance to sudden flow, roughly ρ times wave speed over area. Now the inlet pressure is ZC times the flow, plus the chamber pressure, and the chamber still balances flow as before. In frequency terms, the load impedance is ZC plus the resistor and capacitor in parallel. 3 numbers, and it matches the real arterial load across the whole heartbeat. So 3 numbers, each with a clear job. ZC sharpens the upstroke at the start of the beat, R sets the average pressure the heart works against, and C sets how slowly the pressure decays between beats, the width of the pulse. Change 1, and you change 1 feature of the waveform. Here's how you actually fit it to a patient. The echo gives you a target pressure wave, the dashed curve. You don't know the 3 numbers yet, so you guess, solve the model, and compare. First guess is off. The mean is too low and the pressure crashes too fast between beats because the resistance and compliance are both too small. So adjust and resolve. Raise the resistance to lift the mean. Raise the compliance to slow the decay. Ease the characteristic impedance. Each pass, the model curve creeps toward the target and the error drops. After a few iterations, the green curve lands right on the dashed one. 3 numbers fitted to this patient. So the Windkessel model isn't a black box. Is the whole downstream circulation, boiled down to 1 small circuit, a characteristic impedance for the upstroke, a resistance for the mean pressure, and a compliance for the decay. Derive it once, then fit those 3 numbers to a patient's echo, and you have a boundary condition that breathes like a real artery. So the Windkessel isn't a black box, it's the whole downstream circulation in 3 numbers you can derive and then fit. Next, we tune those 3 numbers to a real patient's pressure wave, and I'll show you the one fitting mistake that quietly wrecks your boundary condition.